All right. Hello again. Third podcast of week 5 for Chemistry 20 is in regards to strong and weak acids and bases. We've already explored how evidence that we got in the labs, which is called empirical evidence, has shown us that the original Arrhenius theory had to be modified, had to be changed to account for the basic properties and the acidic properties of different solutions, which we didn't expect them to based upon the chemical formula. So looking at that then, there's also another factor that comes into play that says, all right, well, perhaps all acids are not created equal and perhaps all bases are not created equal, which comes into the play of what would make an acid strong and what would make an acid weak, and vice versa for bases. Now, there's a couple videos that I want you to watch to start off this lesson, and they've been linked into the notes. So you'll notice, guys, when I link a video, and hopefully you figured this out, a lot of you did for last week from the assignment, you'll see the word video underlined, and it's in blue, and that means that it's been linked. So essentially, you need to hover over it or click on it, and it'll take you to the video I want. Now, the first video that you see is with magnesium. It's powdered magnesium that's put into an acid of, and that one's hydrochloric acid. And then you have another one beside it where powdered magnesium is put into acetic acid. And one of them reacts vigorously enough and produces enough hydrogen gas to actually blow up a balloon. And the other one, yeah, there's a reaction, but not enough to make such an absolute good visual. Now, the next video I want you to watch demonstrates conductivity. It's a super short video. It's less than 15 seconds. But the brightness of that bulb in hydrochloric acid as compared to acetic acid is insane. It's really quite significant. So our two focused acids that we're going to refer to just at the beginning here with strong versus weak is hydrochloric acid and acetic acid. Both acidic, right? And both of them, if you look at this, have an anion with that hydrogen. This has chloride ion. This has acetate ion, CH3COO negative. It's on the polyatomic table of ions, okay? Now, how, even though the concentration of each of those is identical, how do we end up with such a lowly lit bulb with the acetic acid versus that wonderful bright light with the hydrochloric acid? Okay, it's really interesting. Or how do we end up with such a vigorous reaction with magnesium with the hydrochloric acid versus this, still reaction, but quite small with the acetic acid? And let's explore further. Okay. Strength of ionization is a key thing. You already know that when you put an acid in water, it undergoes ionization. So it turns into ions when there weren't ions before. You also know, now according to the modified Arrhenius theory, that one of the ions that's being produced by an acid is hydronium, H3O+. That's important too. Now, this statement is the key one. Not all acids ionize to the same extent. This is huge. Now, the diagram that I have in front of you here, what this is trying to show, and I'll kind of blow it up here so you can see it a little bit better. When you've got a strong acid, you'll see that we end up with the negative ions being totally separate by themselves, right? So here it is originally with the acid going in, and now we have a complete ionization in the strong acid. Vice versa, look at the weak acid over here. On this side, some of the acid molecules stayed together. They didn't actually ionize. So even though we're putting the same amount of acid molecules in for both the strong acid and the weak acid, the difference relates to the amount of ionization. Ding, ding, ding. This is huge. Know this, guys. Strong acids, and this is why they are defined to be strong, will completely ionize with water. So if you look at this chart, and you've got this in your notes, we have, before ionization, our entire amount of hydrochloric acid, 100%, all of it. After the reaction, after it ionizes, look what happens. There is absolutely no hydrochloric acid left. It's gone. The HCl, original, is gone. Every last bit of it has ionized into hydronium and chloride ion. Now, it's something I want you to fill in on your notes here. It's the same reaction equation that we've done all along. We're going to take that HCl, we're going to react it with water, because we know that that's what happens according to the modified Arrhenius theory. Notice this. I haven't emphasized this before, but now I will. A one-way arrow to produce hydronium, H3O plus aqueous, and the anion that's left over, which in this case is chloride. Don't forget to always, no exception, show the proton transfer. With the acid, it goes from the acid to the water. And there we go. 100% reaction, guys. This 100% is our one-way arrow. Nothing is left of what we started with. It's all switched over. Now, when it comes to strong acids, and how do you know which acids are strong? Well, honestly, there's 6 of them, and you need to memorize them, okay? Now, in our COVID-19 world, where technically you're not going to have a big final exam at the end, we will do a big final assignment, take note. However, so the memorization aspect is a little bit different, but be super familiar with this list then. I recapped here how to name these acids because we haven't done that in a little bit. We're going to name these with the classical naming. So if you remember, you have to focus on what the anion is that it's attached to. And this one is perchlorate. So how do we do that then? It's perchlorate, which means it's going to get an ic ending, so ic acid. And then we put the perchlor at the beginning, so perchloric acid. Okay, let's look at the next one. We've got an I, which means there's iodine is our anion. When we have that, we end up putting hydro in the front, hydro, and then it's going to get ic acid. In terms of what goes in the middle, hydroiodic, right? Takes the iodine, take off the INE to put ic acid. Similar type thing when the anion is bromide. So we're going to go hydro, and then it'll be ic acid. What goes in front of the ic? The brome. Hydrobromic acid. Okay? This one's familiar. This is the acid that comes up over and over again. Hydrochloric acid. Okay? Check out the next one. Our anion attached here is SO4 negative, which is sulfate, ATE. 8 gets replaced with ic acid. There's no hydro this time because it's not an anion by itself like we had with iodine, bromide, and chloride. This is a polyatomic ion, sulfate, right? Sulfate. So we end up with no, it's not just sulfic. A lot of you made this mistake. Sulfur's weird. You need the whole word, sulfuric acid. And our last one, the anion is nitrate. Again, ATE. So I'm going to add an ic acid. And for this one, we just have the NIT, nitric, and the R, acid. There we go. Those are your 6 strong acids. Now you're going to have a question in the assignment that says identify which of the acids are strong and which are weak. Well, how will you know which are strong? You will go to this handy dandy list and you will scan it and be like, oh, look, there's sulfuric acid. Check, this one's strong. Yes, it's as simple as that, guys. Don't make it harder than it needs to be. Okay, those are strong acids. Let's talk about weak acids. So again, just to remind you, strong acids completely ionized, 100%. When we get to a weak acid reacts very, very little in water. It still does. It still does ionize, but high majority of the acid stays as a molecule. So we still need to show that yes, indeed, this will react with water. And when it reacts with water, yes, you will still see a proton transfer. That proton in the end will go over to the water, thus producing hydronium, H3O plus, and then we're left with the ion by itself. Take off that hydrogen, you're left with CH3COO. You lost a positive charge, so this is now negative. If that's confusing, look on the polyatomic chart. It shows acetate CH3COO as a negative charge. Now, super, super important. We're so used to putting that one-way arrow, but this is actually wrong now, okay? So take that off. The reason why it's wrong is because of this. less than 1% reaction. Honestly, anything under 100% and a one-way arrow is wrong. What we do instead is a two-way arrow. So you show the arrow going across this way and across this way. Please note, guys, an arrow written like that with arrows on both sides, that's not how we do this in chemistry. It's wrong. You need to show across the top and then across the bottom. This is correct. Okay. When does that happen? Anytime it's not strong. So any acid that's not one of those 6 strong ones is now going to have a lovely two-way arrow. Will I mark you on that? Yeah, absolutely. So pay attention to it, please. From a table perspective, this is similar to our other one. And of course, we still start with the entire acid. This is acetic acid. But notice afterwards, there's a massive amount of acid still unreacted. So most of the acetic acid is unreacted. It didn't ionize, which means we end up with a very low concentration of hydronium and a very low concentration of acetate. Think about the logic of this, guys. If you don't have very many ions present, how could you make a light bulb as bright? You can't. If you don't have very many ions present, if there's hardly any hydronium, there's not as much to react with the magnesium. So it's going to have a much, much less vigorous reaction, and the bulb won't be as bright. Okay. This is just explaining the videos, guys, and that's what I just talked about. Do keep in mind, though, that the concentration of both of those was the same to start with, right? The original concentration was the same. But as for the ionization, the strong acid ended up with way more hydronium, way more concentration of hydronium than the weak acid, even though they start the same, right? You will have a similar question to this in your assignment. So make sure you're keeping it in your head. How does reaction rate, conductivity relate to if it is a strong or weak acid? Think about the amount of ionization that occurs. Okay, let's move on into bases, guys. Now, strong bases are really lovely and easy to recognize. If it's a strong base, it will have guaranteed hydroxide in the formula. And it is as simple as that, okay? So if you see hydroxide in the formula, then you know this is a strong base. And if it's a strong base, we are dealing with dissociation, right? So dissociation, for instance, is what we see happening with sodium hydroxide. Notice the name. The name has hydroxide in it. If you see hydroxide, if it's part of the name, this is a strong base, 100% guaranteed. Therefore, it does not react with water. It simply dissociates into its two different anions, the sodium cation and the hydroxide anion. Notice that it is a 100% reaction. Therefore, we've got the one-way arrow. Strong base, okay? Now, weak bases, on the other hand, are not dissociating. They are reacting with water. And again, it is such a small amount that they react by. Please, I've mentioned this before. I'll reiterate it again. Most anions will act like a weak base. An anion, if you've forgotten, is a negative ion, right? Any negative ion will usually be able to act as a weak base. Now, just a teeny number of them react. It's not very much, hence it's weak. Now, the example I've got for you here is not an anion. It's our weirdo, ammonia. And that's why I keep bringing it up, because it is strange. It's just not one you don't expect to, okay? So ammonia reacts with water. The proton transfers from the water to the ammonia. And think about the arrows. This is a less than 1% reaction. It's weak. So we cannot have a one-way arrow. Must be two-way. We end up with ammonium, has an extra hydrogen, and now it's positive, aqueous. And because, remember how I drew this before, HOH, kind of helps to think of it that way. Because this hydrogen is going to leave the water, we then have hydroxide, OH negative, aqueous. Again, super important. Weak base, two-way arrow, because it didn't react 100%. So weak acids and weak bases get two-way arrows. Strong acids and strong bases get the one-way arrow. All right. Now, guys, if you want a quick example of another one, an anion that would work like this would be something like the carbonate ion, right? CO3 2 negative aqueous. I don't see hydroxide. It would react with water. We would have the proton transfer from the hydrogen to the carbonate. Two-way arrow, guaranteed it's weak. There's no hydroxide there. That's how I know. I look for hydroxide. I put the hydrogen on the CO3. When I do that, it is adding a positive 1. Think about the charges. This is a -2. I'm adding a positive 1. -2 plus positive 1. -1. I still have a negative charge there. Plus hydroxide, OH negative. There is showing how a base is formed from an anion. Two-way arrow, definitely weak. All right, guys, a few more questions, quite a few, that you can start to work on now in your assignment. Do number 4, number 5, and number 6, please. We are going to do one more podcast that relates to pH scale and preventing and dealing with acid-base spills. And then your last question in your assignment is a lab investigation that ties together this pH scale and the strong and weak acids and bases. Talk to you again soon.